Hello, and welcome to MVAO302, Configuring Total Object Manager, or TOM. This is Part 2. MVAO302 is the last in an 8-part series of courses covering MainView AutoOPERATOR. The first area I'd like to cover with you in this session is layering. With layering, TOM provides the means for you to define and manage many similar objects that can run on multiple systems or sysplexes. With layering, TOM gives you the ability to create objects and sets that you can use as models to create objects on multiple systems and sysplexes, and using this process minimizes the administrative burden for maintaining these objects once they're defined. Layered objects are a special type of model object. They're used to generate common objects that you have on many systems, so you can define them once and then you can deploy them throughout all the objects that were generated from the layered objects. So for example, all of your systems need to have a JAS, VTAM, and TSO object defined. If you have 30 ZOS systems, defining and managing all of those objects can be burdensome. Using layering, you can go in and you can modify the layered object that the other objects were built off of, and you can propagate those changes dynamically to all the objects that were generated. A few definitions related to layers. The layer ID is a unique identification number that's assigned to each system within a sysplex. A layered object is a special type of model object who TOM doesn't manage his status, right? He's not actually a running object. He's a group of definitions that you will apply to other objects that are built from the layer. A set, similarly, is a special type of set that contains only layer objects and layer sets. A system layer is a group of layer objects and layer sets that you can define to the sysplex layer. And the sysplex layer contains all of your system layers. You can manage your layers from the EZT layer view. If you need more information about using layers in your object definitions, please refer to the TOM User's Guide. Now let's take a look at configuring TOM's parameters. TOM's parameters live in the HLQ.UBBParm library, which we strongly recommend you share between all of your address spaces. We allow you to go in and specify symbolics so that you can make them configurable so they'll run on all of the systems. To do so, you need to put a process statement in the beginning of the parm member. Alternatively, you can also use the MAM-CFG member to specify different suffixes for members on different systems. All of the parm members that TOM uses are documented internally. If you don't have those comments in the UBB parm copy, you can look at the member in the BB parm that we distribute with TOM. This slide lists the various configuration members you'll find in UBB parm for TOM. The first one, MAM-CFG, controls the suffix for all the additional MAM members that you might want to reference for a specific TOM. MAM-INI has the initialization parms for TOM. MAM-TOM has the TOM parameters that are necessary for the local configuration of TOM. MANPLX has the TOMPLEX configuration parms. MANPLG has the TOM extensions, which today includes your started tasks, STM, and your new Unix system service processes, UPM. And then we have MAMDBG, where you can specify debug parameters, which you should generally only do at the direction of support. Here's an example of the MAM-TOM member. And notice what I've circled here in a yellow box down below. The first statement that isn't commented out is a process statement. It says process sim equals yes, list equals yes. That allows us to use system symbols in the rest of the parameters following. Note below that we have TOM ID equals ampersand sysname and AO ID equals AO ampersand sysclone. This is a pretty common way to configure this member so that it resolves correctly on all the LPARs, and you can share the member between all of your LPARs. Let's take a closer look at the contents of these parameter members. The first one we're going to look at is MANPLX, and this contains the MVAO302 parameters. So the first thing we need to do is assign a MVAO302, the name, which is the MVAO302 equals parameter. We'll tell Tom what XCF group he should use. We tell him what communication method we want to use in the COM equals parameter. We strongly recommend you use XCF when it is available. Here we specify the registry DSN that Tom will be using for his object definitions. We can specify the dump interval, so how frequently we want Tom to take an automatic backup of the registry. We can specify a time of day that we want that registry dump to occur, and then which data sets that we want to dump the registry to. The MANCOM member contains information related to this specific TOM, including the TOM ID, so what is the name of the MV-TOM address space. We also need the subsystem ID for AutoOPERATOR, which goes on the AOID parameter. We need the subsystem ID for the CAS, which is the CAS ID. And then we need to specify an SSID for the logger if you're using an older version of MainView. The MANPLG member is where you specify plugins or which types of objects that Tom should be monitoring. Currently, we support STM for started tasks and UPM for USS processes. The MAM-INI member contains parameters that influence the behavior of Tom. It supports more than 30 different parameters, and most of them can be changed dynamically. The reason we have so many parameters in here is as Tom evolved over time, there were new functions that were introduced and customers wanted the ability to turn them on selectively. So we put them into this par member. Now what we're going to do next is we're going to go over parameters that you probably want to change from their default values. So the first parameter that you may want to change is bounce events. Change it the default from no to yes. And what that does is it tells Tom to honor the start stop events for validation when bouncing objects. Command modify equals always allows you to issue commands against the Tom address space even when the CAS isn't available. Dependency strength equals weak ensures that you have an orderly IPL and shutdown while the child can stay active during the normal course of operations if the parent comes down for some reason and then is subsequently restarted. Force WTO equals yes will direct Tom to send all of his messages to the job log instead of only sending them to MainView logger. This is especially helpful when you're early in your Tom implementation and you're reviewing a lot of messages to debug things. Registry Warning high water mark is set to 0 by default. Strongly recommend that you set that to some value greater than 50. I would suggest 80 is a good starting point. That way if your registry begins to fill up, you'll have plenty of time to reallocate a new one and migrate your definitions over. The stop order parameter is something you certainly want to change. The default is top to bottom. We want to specify bottom to top. And that makes sure that the dependencies are evaluated appropriately and the children are stopped before their parents. Tom supplies a program called AATWeight that's used to do IVPs and to do some testing with Tom definitions. It can be very useful to determine definitions are working before you deploy them into a production environment. The value of AATWeight is that you only need to have one started task defined, and then we can build the definitions in Tom to execute with a job name using the same proc. AATWeight supports several different parameters to control his runtime execution. The first is run equals, which you specify in minutes how long you want this started task to run. RUS specifies in seconds how long you want the started task to run. If you specify append equal to some number between 0 and 4095, Tom will terminate with that append code so you can test your recovery routines. WStart specifies a delay in the startup of the started task, and WStop specifies a delay in the shutdown. And here's an example of the AATWeight proc. You can see the parameters on the proc statement as well as in the parm on the exec statement. So now let's build a model using the AATWeight program. So what we're going to do is, first you can see I have an object called AATWeight in my list. So we're going to go ahead and pull that up. A note down at the bottom where I've circled in a yellow box, we say, is this a model? Yes. So now we can go through and we can define his start event. And this again is for a model called AATWeight. So we tell him what the message ID is. And then for the STC name, we're going to reference a variable ampersand @ STC name. So we can inherit the name of the job that we're going to pass it. And we do the similar thing for our stop event. We give them the IEF404I message, and we specify a symbolic for the originated and started task. And for the append event, we specify IEF450, and again, we have a variable for the started task. And for the start command, what we're going to do is, you'll notice down at the bottom, we have a somewhat complicated looking command, but it's really not that bad. So we're starting the AATWeight program, and then we're passing them the parameters that we talked about in the previous slides. And then we're going to connect those to some values that we're going to show you where they're specified here in a minute. So stop command, again, referencing the symbolic variable. And then here on the dependency panel at the bottom is where we specify the user values that we were referencing in the start command. And the reason we want to do it here is it's a little bit easier to make the changes in these fields rather than having to edit the command. And this way we can use the same command for all of our definitions that reference this model. So now I'm going to create a new object called bmca.gxtrbad, and we're going to use the AATWeight definition as our model. So we'll put AATWeight in the model from field at the bottom. And notice that Tom now shows that the start, stop validation, and append validations are all inherited from the model. If we go to the dependencies panel, we can go down and now we can override the runtime execution for the AATWeight program by modifying the user fields. And you can see our objects added. So now we can do our start, stops, and we can play around. We can build dependency relationships with multiple instances of the AATWeight program and just generally tear it up and really learn the product well. This concludes MVAO302.